quizzes like in front of here. So if you maybe you want to get your copy like during the break. And one more thing is like today we have a friend who joined us like from Fulbright. Yeah. I don't know if this topic is of interest to our guest, in any way, because this is linear algebra, so yeah, probably a little bit boring, but yeah, that's the required course like for computer science student. Okay, so last time, we talked about the first order linear differential equations. So we talked about this, and we went through a little bit of this, and as long as you still have some memory from your freshman calculus, you can easily verify, the solution, will look like that. Okay. But as long as it's your matrix is not defect, meaning there are n eigenvectors, and the corresponding eigenvalues are lambda 1, lambda 2, and so on. Then if that's the case, you can pretty much represent any solution, in this format. And where this C1, C2, and so on, these constants, can be determined if you are given proper initial conditions. So we talked about this last time. So this is an example, but this example is pretty straightforward. As I told you, this section, is in some other semesters I would skip, because it's not exact. Directly under linear algebra, because a lot of people consider this topic under what should I say, 工程数学, another course. So, but I just want to give you some very easy points. So I'll just hand wade through these examples. Quickly. As you can see, you can just get different eigenvalue with different lambda, and you can represent all your solutions in this format, which eventually become like that. So that's like a very simple example. But here's the thing. Starting from here, we are getting into the world of matrices with complex values. So of course, at the beginning we still consider matrices. With real numbers. But now we consider matrix with complex eigenvalues. Matrix with complex eigenvalues. If you consider matrix with eigenvalues, if you have an eigenvalue lambda to be a plus bi, you could imagine, a minus bi will be another eigenvalue, right? Because So if you solve polynomial to get eigenvalue, remember here, okay, because like the matrix we consider, okay, all the elements are still real numbers. Okay, so I mean by using this type of matrix, okay, to get like the characteristic polynomial, okay, obviously your characteristic polynomial, the coefficients are all real, right? Coefficients are all real. Okay, so if you have a solution, okay, with like a plus bi, you must have another solution, like a minus bi, in order to cancel out each other, the imaginary part, right? I mean, from your high school math, right? I mean, you guys learn like complex numbers from high school, right? Okay, so yeah, let's consider x to be the associated eigenvector for lambda. Okay, then obviously your e lambda tx. Okay, the previous discussion, those e to the power of lambda tx. Okay, those previous discussions, I mean, they still work. Even though previously, I mean, it seems like we are discussing. It seems like we are discussing the real number cases, but in fact, okay, all the previous discussion, okay, I mean, those like simple differentiation, those type of stuff, like I mean, it works pretty much the same, like those real number and complex numbers, right? So the same thing can be used. Okay, so e to the power of lambda t times x. Okay, now the lambda is a plus bi, right? Okay, and x. Okay, remember the corresponding eigenvector. Okay, can also be composed of like complex numbers. Okay, so that is why. Okay, now this is x. Okay, the vector x, but we break it into like two parts. The first part is the real number. The second part is the imaginary part. Okay, so this whole thing represents x. Okay, and I mean, if you consider like a lambda, okay, or putting now a plus b, and the corresponding x, like it will be like this. And if it's like the conjugate of lambda, meaning a minus bi, okay, you can imagine. I mean, it's a corresponding eigenvector. I mean, it's also conjugate. Okay. Again, in order to cancel out each other, I mean, the conjugate of lambda, I mean, will have a conjugate like an x. So it looks like this. Okay. So a lot of times we don't like how should I say, like the imaginary part, right? So we could, I mean, you could keep it this way. You could keep it this way. So if the y is like this, now it's like this, I mean, no problem. It's perfectly fine. Okay. If you want to represent your solution, okay, of this differential equations, okay, actually system of differential equation, okay, like that, no problem. But with a little bit more work, we are able to somehow like make them like real. How do we do it? Okay, it's like this. So first, e to the power of a plus bi times t. Okay, let's take a closer look. Okay, this one. Okay, let's break it into two parts. The part with without I mean that hated I. Okay, the part with with the hated I. Okay, we just break it into two parts. So this obvious is like e to the power of at plus bti, right? Right? And then because it's like this is the sum happened in on top, so we know this is like e to the power of at times e to the power of bti. Any question about that? It's okay, right? And I don't know if you read that from calculus or not. Okay, if you don't, okay, let me tell you. Okay, probably it's out of the scope of the linear algebra, but if you have read this previously, that would be great. But not if it's not, I mean, the following will be just like something you probably want to take a look. But if you forget, don't worry about that. It's not going to appear in the final exam. Okay, I will not hold you accountable for that. Okay, so anyway, e to the power of something, for example, xi, can be written as cosine x plus I sine x. Do you know about this? I mean, from calculus, right? No, not from calculus. So from where? 工程数学. Okay, okay, cool. Okay. So, 王嘉信, 王老师, okay, okay. So, yeah, so if you know this, okay, then let me erase this. Then this thing can be written as e to the power of at times what? Cosine bt plus I sine. Bt. Is that right? Is that right? Okay. So then, okay. So you can represent these like that. So consider this thing. E lambda t or e to the power of a plus b t times this thing. Okay, so let me. So this is. E to the power of a plus bit times, okay, real x, you just say real rex I times imaginary x part of x, right? Right? So this is what we want, right? So plug this thing here and then multiply with this. Okay? And then, okay, you have this one, and then you can do some trick like, because then this y1 and y2, they are kind of conjugate, right? Y1 and y2 are conjugate to each other. So what you can do is like, you can add them up, divide by 2. Then you get the real part of this. What is the real part of this? Real part of this is going to be this one times this. Okay, of course, e to the power of at times cosine bt times real part of x. And also, okay, e to the power of at times sine bt times imaginary part of x. Of course, I mean, you have two i's, so it becomes a negation. So it's here, this one. Okay, and the other one, I mean, well, it's like, another one is like subtraction, I mean, half of the subtraction that is imaginary part of e lambda t x. I mean, it's just like to multiply this one with this one and keep the part with imaginary with I. So one is this one times this one, another one is this one times this one. I mean, result in that. Okay. So, well, because this one and its conjugate, they are obviously like, how should I say, like independent. So, you can replace these two solutions with y1 and y2, no problem. Okay. In some sense, like the y1, y2 can be used to reconstruct these two solutions anyway. So these two solutions are kind of replaceable with each other. So most of people prefer representing like a solution in y1 and y2. Okay. And here is an easy example. Okay. So this is the matrix A, looks like that. So if you solve this matrix, for like an eigenvalue, you will find like there are two eigenvalues. One is 2 plus I, another one is 2 minus I. Okay, and the corresponding eigenvector will be this one and this one. I will not go into the detail, okay, because you can do this computations easily by yourself. And from our previous discussion, you just write the solution y1, y2. Okay, basically try to plot this path there and the solution like that. So here, I just want to remind you, okay, I mean, up until now, okay, you can see that, okay, the real matrix, okay, could have like complex eigenvalue and eigenvectors, okay. Actually, in the next section, okay, well, not next section, well, yeah, next section, actually, the next section, okay, we will soon see like you could even have like matrix with like a complex elements. Okay, and we'll discuss those things. Okay, but yeah, let's finish this part first. Remember what I told you? Like in this section, I only want to convey to you two concepts, right? The first one is if you have like a system of linear differential equations, okay? Well, the first order linear differential equation, okay? Then it's pretty straightforward, okay, to solve it. Like, and I show you how to solve it. That's like the first thing, okay? The first idea I want to convey to you. The second idea I want to convey to you is that, okay, once you learn the concept of first order, system of differential equations, you could use that, okay, to solve, higher order system of, differential equations. Okay, that's interesting. That's interesting, like extension. Okay, interesting extension. Here's the example. Okay, so here, okay, you see we have y1 double prime equal to blah 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 this. Y2 double prime equal to blah blah this. Okay, so basically like you have yn double prime equal to the following. So basically like you